Hello, this video is about organic chemistry, which is the study of carbon compounds. And carbon is particularly interesting because it has the ability to form long chains, and that can result in the formation of some really important biomolecules like proteins, lipids, carbohydrates, nucleic acids. So basically all the interesting stuff that we are made of. Okay, so we're going to look at hydrocarbons and their nomenclature first. So there are four types of hydrocarbons: alkanes, alkenes, alkynes, and aromatics. And this diagram summarizes the different types. You might want to stop and take a moment to look at that. Alkanes contain only single bonds, so it's all hydrogen and carbon. Everything's a single bond, that's it. So it's the simplest form of organic molecule. These are also known as saturated hydrocarbons, the idea being that the carbons are saturated with as many hydrogens as you can possibly bond. And there's a few different ways in which we might draw formulas of these large biomolecules. And the first way is one you're familiar with, structural formulas. This is basically your Lewis dot structure that looks like this top one right here. And since these molecules get very large, you might also see the structural formulas written as condensed formulas, as seen right here in the second option. And you might see a super condensed version, which becomes helpful when you're dealing with really complex molecules down here on the bottom. That's known as a skeleton formula. If you look over here, this shows them all side by side. In the skeleton formula, each end or bend in that line, that funny line you've seen right here, represents a carbon atom with enough hydrogens attached to form 4 bonds. So again, 3 different ways in which you might see these structures drawn. Some other things just about alkanes in general is due to what we know about bonding, the carbons in alkanes are all going to be sp3 hybrids because they're all single bonds. That gives them tetrahedral geometry and 109.5 degree bond angles. And the fact that they're single bonds and those are all sigma bonds means that they can rotate freely around those bonds. And that becomes important when you're thinking about isomers and comparing alkanes to alkenes. So they can freely rotate around those single bonds. Alkanes can have things called structural isomers, which are molecules that have the same molecular formula, but the atoms are bonded in a different order. And each isomer is going to have a unique name and properties. So when you're looking for isomers, like if you look at the bottom here are 3 different isomers of the molecule pentane. You want to look for things that are actually attached differently. So you'll notice in N-pentane, that is your straight chain hydrocarbon, each carbon is attached to either 1 or 2 other carbons. This is different than down here in methyl butane. The common name for that's isopentane. But what's different here is you'll notice there's this one carbon right there that is attached to 1, 2, 3 other carbons. So that gives it different bonding, it's different structurally than pentane, even though it has the same number of atoms in it. Down here on the bottom, dimethylpropane, if you look at this carbon in the middle, it's attached to 1, 2, 3, 4 other carbons. So again, it's structurally different. The bonding is different in these 3 varieties. And notice how they have various properties. They have different melting points and different boiling points, for example. And different isomers will have different names. If 2 things are if they're not isomers, they'll have the same name. So, looking at organic nomenclature, you can break a name down into 3 parts. I like to start at the end and work my way backwards. So the ending, the suffix, tells you what family it belongs to. So, is it an alkane, is it an alkene, alkyne, etc. The base tells you how many carbons. So there's 1 carbon, 2 carbon, 3 carbons. We have different names that go along with those numbers of carbons. And then sometimes you will have a prefix as well, which is if there's things branching off of that carbon chain. Maybe it's a halogen, maybe it's some other carbons. So sometimes you'll have a prefix, not always though. So again, this is another table kind of summarizing that. So if you're just thinking about your hydrocarbons, Now you've got three possible suffixes. Could be alkane, alkene, alkyne, and then your number of carbons gives you the base name, and that's 1 is meth, 2 is eth, 3 is prop, 4 is but, 5 is pent, 6 is hex, 7 is hept, 8 is oct, n is non, 10 is dec. So if you have a 10 carbon alkane, you call it decane. Or if you had a 3 carbon alkene, you call it propene. And you may have prefixes if there are different groups branching off of your hydrocarbon chain. If it's a halogen, what we do is we take the name of the halogen and we change the ending to O. So like chlorine becomes chloro, bromine becomes bromo, fluorine's fluoro. Then you have alkyl groups. So the name of your alkyl group is based upon the base name for that number of carbons. So if you have a single carbon branching off your chain, it's called a methyl group. If there's 2 carbons, it's called an ethyl group. So we're looking down here now. And if there's 3 carbons, propyl, 4 carbons, butyl. You could go down the whole list. So these base names can be converted into alkyl names. We call those alkyl groups. How to name a compound: you find the longest chain in your molecule and you number the chain from the end nearest the first substituent encountered. So notice in this example we have a 6 carbon chain. I can either choose to start numbering from the left or from the right. I'm going to choose to number from the left because that's the side closest to my methyl group right there. So when I'm naming this, starting from the end, the suffix will be ane because it's an alkane. The base is hex because there are 6 carbons in my alkane chain. I have a methyl group branching off of it, and that methyl group is branching off the second carbon. So it's 2-methylhexane. If there's more than one type of substituent, we list them alphabetically. So in this example, we have ethyl groups and methyl groups. So notice how I wrote the ethyl group first. And if there's more than one of a certain substituent, we use the prefix di, tri, tetra. So in this example, we have 1, 2, 3 methyl groups. So we call it trimethylheptane. And notice that each substituent gets its own number so that you know where they all are. So the ethyl's on the 3rd carbon, and I have methyls on the 2nd, 4th, and 5th carbons. So halogens are another common substituent. So let's look at some more examples with this. So we're looking at skeleton formulas here. So this one on the upper left, I've got 1, 2, 3, 4 carbons in my chain. And I'm going to start numbering from the left because that's the side closest to my chlorine. 1, 2, 3, 4. So it's an alkane. It's got 4 carbons, so it's butane. And it's got 2 chlorines coming off of it, so it's dichloro. And those chlorines are coming off of the 1st and 3rd carbon. So it's 1,3-dichlorobutane. This one here, I've got 1, 2, 3, 4, 5. I'm going to start numbering from this side because that's closest to my chlorine groups. So this is an alkane. It's pentane because there's 5 carbons, and it's 2,3-dichloropentane. And this example right here, I've got 1, 2, 3, 4, 5, 6. This one, let's see, which side should I number it from? So I can start numbering from the left or from the right. Looks like I should start from the right because that's nearest my bromine group there. So 1, 2, 3, 4, 5, 6. So the base of this is hexane. Whoops, and it is 1 bromo 4 ethyl hexane. Because notice how this is a 2 carbon group branching off there. So if it's 2 carbons, we call that an ethyl group. 1 carbon's methyl, 3 carbons propyl, etc. You can have cycloalkanes. So for example, you can have hexane would be 6 carbons in a straight chain. Cyclohexane would be 6 carbons linked up in a ring. You tend to see this most commonly with 5 and 6 membered rings. Those are most stable and give you the best angles. Smaller rings tend to be really strained, so they're not as common. And with naming them, you just put the word cyclo in the front. Okay, alkenes are ones that contain at least one carbon-carbon double bond. We call them unsaturated. And because of that double bond is locked in place, so they can't rotate freely around the bond. So it becomes significant when you're thinking about isomers. And as a result, you end up with these things called geometric isomers when you're dealing with alkenes. And these geometric isomer possibilities are called cis and trans. And you've probably heard of trans fats, people talking about those in the news. This is what it means to be cis or trans. If you are a cis alkene isomer, that means that your two groups in question are on the same side of the double bond. If you're a trans isomer, the two groups attached are on opposite sides of the double bond. And since that double bond is rigid and locked in place, this becomes significant and can affect their properties to varying degrees. And speaking of trans fats, here's a picture that kind of shows you some various things related to fats you may have heard of before. So you may have heard of people talk about saturated fats. Remember, saturated means all single bonds. Okay. And, whoops, all single bonds. All right, that stopped working. And your unsaturated fats will have at least one double bond in them. You can have cis unsaturated fats, which you don't hear people talking about much, or trans unsaturated fats. And the cis version is what can show up naturally as in vegetable oils. And these trans fats, notice in the trans fats, your hydrogen's branching off opposite sides of the bond, versus the cis, they're coming off the same side of the double bond. Notice how that's affecting the shape, and shape determines properties, so they can behave differently, and they seem to do so in your body. So that's the difference between a cis and a trans fat. Alkynes contain at least one triple bond. And thinking about naming alkynes and alkenes, notice in this name, we've got two numbers in here. We've got a 4-methyl-2-pentyne. And the reason why is you're going to look at your longest chain that contains your functional group. You think of alkyne as being like a functional group here. And you want to number it from the side closest to your functional group. So it looks like this. And what we'll see is that there's a methyl group branching off the 4th carbon, and then your base is pentyne, but this triple bond right here could show up in more than one place. Like if I just wrote pentyne, you wouldn't know where that bond is. It could be here, it could be here. So we need this number right here to tell us that the triple bond is happening at the 2nd carbon. So that's what this number tells you, is where that triple bond is located, because there is more than one possible isomer of 4-methyl-pentyne, or just of pentyne in general. Here's a page, summarizing the different hydrocarbons. Some examples of that. Aromatic hydrocarbons. These are cyclic hydrocarbons. They look a little bit like cyclohexane, but what's different about them is they have alternating double bonds, and that results in a resonance structure. And these are a chemically important group, and we tend to name them based on the common name. So C6H6 is benzene, and so we name things as benzene derivatives. So there's some examples down here. So you just want to recognize benzene. And then up here we've got some examples of the other cycloalkanes. So this is it for hydrocarbons, and I'll have another video up on other functional groups.